The first thing we're going to look at when examining a vibrating system is determining the natural frequency of the system. So I'll show you a couple different methods of how to calculate the natural frequency. The natural frequency is a property of the system, and it's something that's important to know. Our first method that we're going to look at is using the equation of motion, and we can use our equation to set up the form of the solution. So this is our first method. Using sum of the forces is ma. So let's look at a typical system here with a mass and a spring, and we're going to say that the mass here had some initial position that was unstretched. When you add the spring had an initial position that's unstretched. When you put the mass on it, if there's gravity involved, it'll stretch it a little bit to an equilibrium position, and we're going to call that displacement equal to delta. So this is when it's still, and if you examine the system at its current state, we have the force of gravity on the system and the spring force pulling back up, and we set up our equation of sum of the forces equal to 0 at equilibrium, and the balance of forces shows that the weight, or the mass times gravity of the mass, is equal to k, the spring constant, times the displacement that it's made. Then we're going to pull it a little bit farther in order to release it to start our vibrating system. So if you stretch it another distance x, we have a little bit more load on the spring, and when you release it, it'll vibrate up and down, and as it moves, x will change from positive values to negative values, and back and forth from there. So let's look at our equation written out using our equation of motion, F equals ma. So the forces acting on the system are the gravity pulling down, the force of the spring pulling back up, and if we write out our equation, we have here that we have the mass and gravity minus k delta. We're using a downward direction for our positive, and minus kx is equal to mx double dot. That's our mass times acceleration. But note that the first two terms are equal to each other, so those drop out, and all we're left with is a minus the force of the spring equals the mass times the acceleration, or another way that we can write it out is the acceleration plus k over m times the displacement is equal to 0. And that's kind of one of the more general forms that we'll be looking at. We're going to rename that k over m as our natural frequency squared. And the solution form for this differential equation comes in the form of a sine and cosine combination. A and b are the magnitudes of the sine and cosine components. And when you're looking at what a and b should be, we can use our boundary conditions on the system, and basically that would be at time 0. We could say that there's some initial position, x at 0, and that should be equal to b when you plug in time as 0. Right, the cosine goes to 1, sine goes to 0. Another one is the initial velocity. Same type of process, take the first derivative and then set time equal to 0. And the cosine goes to 1, so we have an a omega n, and the sine goes to 0, so the b drops out of that one, so we have an initial velocity of a omega n. And so you can write out your final form of the equation of motion, or the displacement, as x is a initial velocity of omega n times the sine of omega t, plus an initial position times the cosine of omega nt. And that's pretty much the general form that we have in a simple single degree of freedom system. So a couple definitions we can look at. Omega n is technically called the circular frequency, or the natural circular frequency, and that's calculated as the square root of k over m. There's also a period that we could look at, the natural period tau, which is found from omega n and 2 pi. Basically, the period is equal to 2 pi times the inverse of the natural circular frequency. And technically the natural frequency would be the inverse of the natural period. This is one that we can look up or that we can use, but we don't usually refer to it this way, but that's something that we can use. Omega n would be in radians per second, and the frequency f would be in cycles per second. That's the difference between them. Just to note a few things about this is that if you look at the formula, it only is determined by the stiffness of the system and the mass of the system. There's no other terms in there besides 2 pi, but it doesn't the natural frequency is not determined by how far you stretch the spring or if there's a force acting on the system. It's only determined by the stiffness and the mass. So it's a property of the system that's independent of the loading on the system or the motion of the system. We're going to be looking at starting off with single degrees of freedom systems. The degrees of freedom are the motions that the system makes as it's vibrating. So they're looking at independent motions. For a single degree of freedom system, there's basically one motion. That's an example of the mass spring system that we just looked at. Shows that there's only one motion, x, that we're examining. So it's a single degree of freedom. We'll also look at some multiple degrees of freedom in the future, and that's when we have more than one motion that's independent of each other, and we could set that up as potentially maybe a ground with a couple of masses with springs in between. Maybe the ground can move and both springs can move, and all those motions are independent of each other. You can move x2 without necessarily having x1 and x3 move. So those would be multiple degrees of freedom. Those are a little more complicated to look at, but we'll look at some later on. So I'll show you another example in a minute, so watch the next video, and we'll look at a different way to solve a natural frequency.